welcome to our next video where we are practicing some questions in topic 4. This is the second part of topic 4. Topic 4 comes in 3 parts just to make it manageable, where we introduce the normal distribution, hypothesis testing, and all of that in one topic. So this is the second part that I'll call 4.2. This is our second part also where we do examples not by hand but with the aid and convenience of a spreadsheet. I'm using Microsoft Excel, but others would work as well, just to give you some options, but we are essentially doing the same thing as the video named B1. We are looking at question 14, which is here on page 136. If I show the page, where's the page? There, 136 in our book that we have used in the B1 video as well. I encourage you to watch that video first because we've read the question already, we've worked through the question already, so we might go a little faster in this one because there's certainly an order that I expect one to watch these videos in. So let's read through it quickly anyway. Based on the information given for each of the following studies, decide whether to reject the null hypothesis. For each, give the z-score cutoff on the comparison distribution at which the null hypothesis should be rejected, the z-score on the comparison distribution for the sample score, the observed z-score, and then my conclusion. So we've done study A and study B. So let's now do C and D. Instead of using a calculator and writing everything by hand, we'll do the same thing, but we'll use a spreadsheet instead. So I have a very rough, normal distribution here. Got away from me a little bit. Just to have something to look at when we think about cutoffs and the areas under the normal curve and so on. So this will be study C, where we have a mean of 5 and a standard deviation of 1. So let's put that in here. Mean, I'm going to call it mu. 5 and sigma 1. These are input cells. My habit is to color them yellow so I can spot them nice and quickly. We have our sample score of 7. We have an alpha, they call it P for reasons we get into when we look at SPSS and our more dedicated statistics software. This is our alpha, 0.01. So let's write that down here. We have our raw score X, which is 7. Our alpha value is, let's just say 1%, or you can go 0.01. I guess that's maybe better. These are also inputs, boom, that we may use in formulas that come up, maybe not. So now we have in C, one-tailed test on the high side. So our null hypothesis is testing whether the true mean is more than this population mean of 5. So let's maybe write down, where should we put it? Over here maybe, our H0. Let's just do it like that. Is testing whether, let's call it mu1 is greater, assuming it's the same, 5, and our research hypothesis is then, no, it is greater than 5. So does the evidence, a raw score of 7, serve as strong enough evidence to suggest that the true population mean is actually greater than 5. That is our rough setup. Now we're not working through writing down all the steps of the hypothesis testing procedure. We're going to get to that a lot. Right now it's just the logic and the thinking behind it. So first I want my Z cutoff. Let's write it like that. And what does that mean? That means, actually, let me do the observed one first, because we have the information right here. So when I have a raw score of 7 and I standardize it, the observed z-score is just the corresponding z-score of that, and that will follow. There isn't the precise formula with the notation, but it's, I guess, 3-1 is the closest, where we use the population values here. The raw score minus the mean over the standard deviation. So let's do that and say raw score is 7 minus mu divided by sigma. And I get a 2, which is a very nice, convenient number. So I observe a z-score of 2. I'm going to color it green because it is a formula, it is a calculation to remind myself it used other cells to get its value that it's showing. Now I know this is now, let's be precise here. I'm doing the B part first. We can do whatever we want. Let me just move this down one, and that's the B part first. But because I had the 7 right there, convert it right away. It's right there. Now we want to find, well, if alpha is 1%, what is our cutoff of z-score? So we're on the high side here, so we're looking for a line. Let's put in a little line there. Why not? My drawings are so wonderful. Why stop now, right? So that'll be my Z cutoff. Z cutoff. Let's move it a little bit. Not much, but a little bit. So that over here is 1%. And on the other side is then 99%. I want to know what is the z-score that cuts it into these two pieces. Well, when we did it by hand, we looked it up in our table. And we looked at the tail. We're looking for 1%. We went all the way to 1%. 1, we're getting there. And it wasn't exactly there. So we had to make a decision, rough rule of thumb. Do we take the more conservative one? Do we average out the 2? Luckily with the spreadsheet, we have the table built in as a formula, and it is precise. We just have to find it. So let's go and find it. So this is a normal distribution. I'll search for the word normal in case I don't have an idea what the formula name is. I scroll down a little bit and I look for the standard normal, the ones with S. There are others as well, but I'm using the standard normal ones to closely represent what we did by hand with the table. So we have these two, normal distribution, norm.s.dist, and norm.s.in for the inverse. So the first one gives me a little description here. It wants the z-score, and then, always cumulative, returns the standard normal distribution, the percentage. But we have the percentage. It's 99 and 1. And we got that by way of alpha. we want the other one, where we give it the probability on the left side, which will be 99%, and it gives me the cutoff. Now, there's a couple of ways you can go about this. We can simply put in 0.99. Remember that in a calculation, technically, you never use a percentage. You always use the decimal version. The percentage is a presentation thing. It's not actually what we're using. 99% when used in a calculation is 0.99. And you see here, I get my 2.32, which we sort of guessed, but we didn't know exactly. It's not the average either. It's 2.32635 to be precise. So by using this, we're not using statistics software, but we kind of are inching in that direction. We can just be much more precise because the complete table, quote unquote, is in this spreadsheet software. Whereas what you have in the book is an abbreviated version with gaps. Okay, let's color that green. Now there are other ways we could have done that. I'll just put it over here. We could have said, let's say inverse formula, because we used it, it's up in the list of frequently used functions, so that helps a lot. We could have said here in the probability we want our alpha, and then we would get the negative side, right? Because of the symmetry, it is always going to look at the left side. Unlike our table here, we're always going to have the left side of it, but that's not a big deal. Then I just drop the negative. It's exactly the same absolute value, right? So you don't have to do much. Just remember what the function does. It's always looking for the left side of the cutoff line. All right, so there we have our cutoff, and then we can make our decision. We can still write a little bit, and we see now that our observed score of 2 is to the left of the cutoff line. So we can say here, since z observed is less than z cutoff off, we do not reject, let's say, a h0. And we can say a little bit more. The evidence, which was this raw score of 7, is not strong enough. Or we can say inconclusive. The null hypothesis might be, in fact, false, but the evidence doesn't really suggest that. So if this is the distribution and we get raw score corresponding observed z-score far extreme, far to the right in this case, that would tell us that, look, this doesn't just happen by chance. It's so unlikely. Yes, there is a small chance, 1%, that in this distribution under the null hypothesis, we can get something that extreme. But it's much more likely that this is happening because the true distribution has a mean further to the right, and those numbers are therefore more common, those scores. So that is sort of the idea behind our hypothesis testing and how comparing the observed and the cutoff scores are used. All right, well, we have one more. Let's maybe copy this to the end and call this study D. Now, of course, a lot of this is the same. A lot of it is not the same. I'll just erase a lot of this and a lot of that and a lot of that. we more or less have the same setup. So I just want to be a little bit more efficient by getting the same template that will fill in. But if we look at the question, study D, same mean, same standard deviation, same sample score. So that's good. Same alpha, but now we have a two-tailed test. So our null hypothesis, I'll put it over there. Our null hypothesis again is mu1, the population that we're investigating, is in fact 5 versus it is, now I don't have a not equal sign, not equal to 5. Let's just write it like that. Maybe I do, but I don't want to insert math symbols or anything right now. It's equal, not equal. So now our z cutoff positive, let's put a little plus in front here. No, don't do that. Just like, okay, fine, fair enough. I don't want a formula. I just want a little plus sign. Thank you. Versus the negative side, I now have two sides, if you can excuse my extremely rough drawing, because I have a two-tailed test. And now in the middle here is 99%, and on either side will be half of 1%, so 0.5% on this side, 0.5% on that side. It's good to just no, don't round it. Why would you do that? Unfortunately, sometimes the new software tries to think too much for us. It did that one right. Let me just make it look the same by rounding to 2 decimal places and showing enough decimals. It doesn't always present it the way I want, but in the background it was always 0.5%. So in a two-tailed test, I'm looking at this situation. Regardless, our observed score is done the same way. Let's do it again for practice. I'm calculating. I'm taking the observed raw score, subtracting the mean, taking all of that and dividing by the population standard deviation. And of course I get a 2 again. Everything is the same. Now my cutoff is not the same. Now in the case of the table, in my book, I could look at the tail and I'm looking for 0.5. Let's just see how it compares. I see 0.5 there, and yet again, I get a 0.51 and a 0.49. What do? Do I average 2? That's probably what I would do. Some argue that no, I should be more conservative and go for the 2.58. Regardless, it's a little inconvenient. The book doesn't have that many pages, so this is a summarized version with gaps in it. Luckily, the built-in formula, which essentially does the same thing, doesn't have any issues like that. I just have to remember what it was. Now, perhaps you have it as frequently used functions, or perhaps you don't. If you don't, you can just search for a normal. Scroll down a little bit. You're looking for the S, because it's this, the standardized normal, the z-scores. Which one do I want? Well, do I have a z-score and I'm looking for the percentage, or do I have a percentage probability and looking for the corresponding z-score? Yeah, that's the one. So now what do I put in here? It's always cumulative. It's always from the left to a cutoff. Now I can go just say 0.5. That's not quite right? Because this is a percentage. And when I use a percentage in a calculation, it has to be the decimal version. And the decimal version of 0.5% is, you take this and divide by 100, so 0.005. Or you can go to the positive cutoff line. It really doesn't matter. You just want a cutoff line because of the symmetry. It's going to be the same. So the 1z cutoff is negative 2.57583. My book didn't have space for that. And the other one, I'll just type it in, 57583. I have two sides to it, right? Because it's a two-tailed test. Now you could have also, next to this alpha, done a cumulative distribution, cumulative decimal version of the percentage, and said here, well, it's two-tailed, so I'm going to divide that by 2, and that is the same as the percentage we have here, but the decimal version. And then you could have said, let's just insert my same function. I could have then taken that as input instead of having to do it in my head. Totally fine. You do have options. Just be aware of how percentages are used and what that function is doing. So we're ready for our conclusion. Now we see that the cutoff z-scores, because of the two-tailed test, they're actually further out than they were previously. So unfortunately, we're not going to reject. Let's say here, since our observed z-score is less than, I'll say here, the positive z cutoff. There are two of them. In this case, I'm on the positive side, where my observed z-score sits. We do not reject the null hypothesis. The evidence is not strong enough. Result inconclusive. Remember, we are never accepting the research hypothesis. We're never saying yes. Sorry, let me rephrase that. We're never accepting the null hypothesis. Sorry. We're never accepting the null hypothesis and saying, yes, the true population mean is in fact 5. All we're saying is the evidence that we are getting is not strong enough to suggest that it's not 5. It may not be 5. It may be just a little bit different than 5. We don't know. We can only go on the evidence, and the evidence does not suggest that the mean is anything else. I could have, under this mean of 5, I can get scores of 7. It's perfectly normal. Within acceptable fluctuations around the mean, 7 is a quite common score to get. So it's not extreme enough to suggest that, in fact, maybe a different distribution is behind the scenes here. 7 is quite common to get, so the result is inconclusive. The evidence is not strong enough. We do not reject the null hypothesis. All right, so that should give you a little bit more practice in terms of the thinking behind hypothesis testing in this basic setup, this basic distribution, where we just practiced the same questions with a spreadsheet calculator, essentially, for convenience. What we're doing does not change at all. Just extra practice, which is always a good thing. All right, we will slowly move on to the next topic, but that'll have to wait for another video. Until then.